Hello everyone, welcome back to the second class of week 9. In the first class, we have seen that the statement of the Taylor's theorem as well as the Maclaurin's theorem. The Maclaurin's theorem can be deduced from the Taylor's theorem by putting a equal to 0. And for the both theorem to be valid, the function and its n minus 1th derivative is continuous in a closed interval a to a plus h, as well as differentiable in an open interval a to a plus h. Now, it is the time to use the application of those Taylor's theorem and Maclaurin's theorem and to solve some of the complex problems. So, I have chosen some problems on Taylor's theorem here as well as the Maclaurin's theorem and how we are going to use that one. So, this lecture is totally based on the problems and their solution using the Taylor's theorem. So, we will try to explore the Taylor's theorem as well as the Maclaurin's theorem and their applications in solving the problems. So, the first question, use Taylor's theorem to prove that 1 plus x by 2 minus x cube by 8 is less than a square root of 1 plus x is less than 1 plus x by 2 if x is greater than 0. So, here inequality is given and you have to prove at least two inequalities. The first inequality say that a square root of 1 plus x is greater than 1 plus x by 2 minus x cube by 8, and the second inequality says that 1 plus x by 2 is greater than 1 plus a square root of 1 plus x. Now, look at the structure. The structure is such a way that in the left hand side, if you just subtract x cube by 8, the whole quantity is become less than that one, and if you are not subtracting the inequality, the 1 plus x by 2 it become greater than of a square root of 1 plus x, right? How to solve this one? So, taking this function, since we are working on this one, so let take the function f(x) equal to a square root of 1 plus x, where x is greater than 0, right? So, this function is derivable and we can find out the first derivative of this function f dash of x. So, what will be the first derivative? 1 by 2 into a square root of 1 plus x, this one. The second derivative, use the same one, 1 by 4 1 plus x power 3 by 2. The third derivative, that means 3 divided by 8 1 plus of x 5 by 2 and so on, right. So, by Taylor's theorem with Lagrange form of remainder, you had already known that, right. Putting p equal to n will give you the Lagrange theorem. For any x is greater than 0, f(x) equal to f(0) plus x into f dash of 0 plus x square by factorial to f double dash of 0 x cube by factorial 3 f triple dash into c for some c belongs to 0 to x, right. So, this Taylor's theorem is now become Maclaurin's one, right, because the interval we have chosen is 0 to x, and putting this one whole value, the first will become f(x) equal to a square root of x plus x. So, that means a square root of 1 plus x, and this will become 1 plus of x by 2. See here, f of 0 here 1 by 2 square root of 1, right, f double dash of 0 1 by 4 into 1 plus x power 3 by 2 and so on. So, this will become 1 plus of x by 2 minus x square by 8 plus of x cube by 16 1 plus c 5 by 2, right. And therefore, for x is greater than 0, 1 plus square root is greater than of this inequality, where you will have the third term of this equations. And by Taylor's theorem, Lagrange form the remainder after two terms for any x is greater than 0 by x square by 2 factorial double dash of d. And so, a square root of 1 minus x can be written as 1 plus of x by 2 minus x square by 2, and for x is greater than 0, this will be less than of this because this is the extra term. So, a square root of 1 plus x is less than 1 plus of x by 2, right, and hence from 1 and 2 we have 1 plus x by 2 minus of x cube by 8 is less than square root of 1 plus x, and which is less than 1 plus of x by 2. So, that is how the Taylor's theorem play a role to solve the questions as it required. Now, look at the question first and then try to find out the answer. So, let C be any real number and f be a real function such that f double dash is continuous on some neighborhood of C. So, here f of n minus 1 is given, f of n minus is equal to f double dash, at least it is given, right. Prove that limit h tends to 0 f c plus h minus 2 into f c plus of f c minus h divided by h square is equal to f double dash of c. So, here the question has been not asked only directly for the Taylor's theorem, but it has been asked for second derivative of the function, right. Now, we have to prove left hand side in a limit form, and in the right hand side it is given as a second derivative or higher derivative of f at the point C. So, let f double dash be continuous in a closed interval actually. Anyway, so on an open interval C minus delta to C plus delta for some delta is greater than 0. So, we have taken C here and we have taking this as a neighborhood, right. So, we have taken these 3 points, right. And by Taylor's theorem with Lagrange form of remainder after 2 terms for any h satisfying 0 s to delta, we have fc plus h. Fc plus h becomes fc plus of h into f dash of c plus h square by factorial to f double dash of c plus theta h, where theta lying between 0 to 1, right. Similarly, fc minus h is equal to fc minus of h f dash of c plus h square by factorial to f double dash of c minus theta h, and where theta lying between, not theta dash, but theta lying between 0 to 1, right. Now, add these two terms. So, adding these two terms fc plus h plus fc minus h, see, fc plus h plus of fc minus h, and this one will be minus 2 fc is equal to h square by factorial 2 into f double dash of c plus theta h f double dash of c minus theta h, not theta dash h but theta h, right. So, fc plus h plus fc minus h minus 2 into fc divided by h square is equal to 1 by 2 f double dash of c theta plus h and f double dash of c c minus theta h. Since f double dash is continuous, we had already assumed here f double dash is continuous on some neighborhood of c, right. So, that is why f c plus theta h can be converted as f double dash of c, and similarly f double dash of c minus theta h can be converted as well f double dash of c, can be assumed like this. Why? Because f double dash is continuous in a where? In an open interval of delta neighborhood of C. C is here and you have a delta neighborhood of this, right. So, that means f double dash of C is nothing but these are equal to these two, right. So, in a limiting sense. So, now the limit of left hand side is this one given fc plus h plus fc minus h minus 2 into fc divided by h square is equal to f double dash c of the right hand side, right. So, that is a good question, that is a theoretical question we call it, and proving a higher derivative of a function which higher derivative is continuous in some neighborhood of C, our point C, it will be important to understand that it is only possible due to the Taylor's theorem and in the Lagrange form of the remainder for a second term, whatever it has given or it has been asked in using this one, right. Now, If you understand the previous question and their solutions, you may try to find out the answer of this. So, let C is a real value constant and a f be a real valued function defined on some neighborhood in A of A such that f double dash of is continuous at A and f double dash A is not equal to 0. So, this is not C, this is not C, but this is A. So, let A be a real number and f be a real function defined on some neighborhood in A. So, defining some neighborhood this and we call it N. So, let me change the color first. So, this one is your defining value, the neighborhood of this value, and then prove that limit h tends to 0 theta equal to 1 by 2 where theta is given like this. So, here is the theta is given. Since f double dash is continuous at A, f double dash exists in some neighborhood A minus delta A plus delta and this is the subset of this neighborhood, right, because you have chosen this one. This is the delta and Na is the neighborhood. So, A minus delta to A plus delta open set is a subset of Na. Now, looking for a different type of cases and then try to find out the answer. Theta is given, theta is f a plus h is equal to f a plus of h f dash of a plus theta h. It is a implicit form of the theta is given. So, case 1 when h is less than delta. So, I am taking h as less than delta. So, I am looking for this h. I am looking for this h is less than delta. So, by Taylor's theorem with Lagrange form of the remainder after two terms we have f a plus h is equal to f a plus h f dash a plus h square by factorial 2 into f double dash a plus theta h where theta is nothing or theta dash. Okay. So, theta dash here it is customary to take in this theta dash. So, let me erase this. Okay. Theta dash is another symbols. So, f dash of 0 to theta dash to 1, but you will be confused with this one. So, I think it will be much better if I use this theta only. So, f double dash of a plus theta h 0 theta to 1, you may taking this one as theta only. So, f dash of a plus theta h is equal to f dash of a plus h by 2 factorial f a plus theta h. Applying mean value theorem to f dash on the interval a to a plus theta h, we have f dash of a plus theta h is equal to f dash of a plus theta into h f double dash a plus theta h 0 to theta double dash of 1 and therefore half of a f double dash a plus theta dash h is equal to this. Taking this limit you will get as f double dash is continuous at a, you will get the required answer, that is 1 by 2. That is since we are looking for neighborhood of a or h neighborhood of a. So, a is here, h neighborhood is here, delta is bigger than that one and Na is any neighborhood of this. It is given f double dash is continuous on a neighborhood, that means it is continuous in that interval. It is also continuous in that interval as well, right. So, that is why the whole quantity is going to be half. Similarly, if minus delta is less than h, then we have theta equal to half. Proceeding in the similar manner, we will give the answer as theta equal to half. So, look at in the last questions, I believe that it is these theoretical questions boost up your concept. So, look at one of the numerical problems. So, f x equal to sine of x. Prove that limit h tends to 0 theta equal to 1 by root 3 where theta is given by f h equal to f 0 plus h into f dash of theta h where theta lying between 0 to 1. So, f h equal to f 0 plus h f dash of theta h and that will give you sine f of h. F of h is what? F of h equal to sine of h. is equal to f of 0, sine of 0 equal to 0, plus h into f dash of theta h. F dash theta is equal to cos of theta h. That is what we had, and theta lying between 0 to 1, right. So, that will give you f h equal to f 0 plus h f dash of 0 plus h square by 2 factorial double dash of 0 plus of h q by factorial, okay, h q by 8 into f triple dash of theta dash of h, right, and here 0 theta dash less than 1. So, f double dash of theta h can be written as f dash of 0 plus theta into h f double dash of 0 and plus theta square h square by 2 factor f triple dash of this, and using all those you will get sin h is equal to h minus h q by 6 into cos theta dash of h, and henceforth cos theta h equal to 1 minus of theta square h square by 2 cos theta double dash of theta into h. So, from these 1 and 2 we will get cos theta h is equal to 1 minus of h square by 2 cos theta dash of h, and theta dash lying between 0 to 1. So, from 3 and 4th we have 3 theta square cos theta double dash theta h equal to cos theta dash of h, and limit h tends to 0 cos theta dash is equal to nothing, but it is 1, and the another one is also 1, and henceforth cos of theta, from here you will find out cos of theta is nothing but h tends to 0, theta equal to 1 by root 3. So, 3 theta square equal to 1. So, theta equal to 1 by root 3, but it is in the limiting case, it is in the limiting case, right. So, that is the all problems. So, we have explored 3 theoretical problems and 2 numerical problems, starting from, as you can see from this start one, yeah. So, this one where we had showed that given function square root of 1 plus x is less than sum of the numbers, that is 1 plus of x by 2, and it is greater than if I add the another terms. So, it totally depends on how many terms we are adding in Taylor's theorem or as well as the Maclaurin's theorem. So, can we go once again for this one? So, if I put f of x, let me change the color first. So, if I put f of x as a square root of 1 plus x, then f dash of x can be calculated 1 by twice square 1 plus x. Similarly, f double dash of x can be calculated 1 divided by 4 1 plus of x 3 by 2, right, and f triple dash of x can be calculated 3 by 8 1 plus of x 5 by 2, and so on and so on, right. Now, I am interested to only taking a remainder term after 3 terms. So, Lagrange form of the remainder terms after given 3 terms only. So, for this since x is greater than 0, f x can be written as f of 0 plus x into f dash of 0 plus x square by factorial 2 f double dash of 0 plus x cube by factorial 3 f triple dash into c, some number, right, lying between 0 to x. So, that means f of x, how much the value it was? It is written as a square root of 1 plus x, and f0, what will be the f0? f0 is equal to 1 plus of x into f dash of 0, f dash of 0 you see here, f dash is equal to 1 by 2, and plus x square by factorial 2 f double dash of 0, f double dash of 0 equal to, this is 1 by 4, x square by 4, right. So, now you can see this will comes out to be x square by minus of 2 into 4 8, and plus so on, this one x cube plus of so on. So, here it is written, right. So, a square root of 1 plus x is equal to 1 plus of x by 2 minus of x square by 8 plus of x cube divided by 16, 1 plus of c 5 by 2. This is the remainder term. This is the remainder term after 3 terms, right. Since x is greater than 0, that means a square root of 1 plus x is greater than 1 plus x by 2 minus of x square by 8, because this is the positive number. This is the positive number. So, this is greater than. Similarly, since x is greater than, therefore, a square root of 1 plus x is less than 1 plus of x by 2. That is what we have done by taking only 2 terms. Taking the only 2 terms, we get the one remainder term here and getting the answer, right, this one. So, that means it is always greater than 1 plus x by 2, and henceforth this inequality holds. So, and then the second problem was to find out if double dash of C for a double dash is continuous on some neighborhood of C, and then by the limiting value we have shown that it is the case where fc plus h minus 2 fc plus fc minus h divided by h square is equal to limiting function of f double dash of C, right. Seen here, we have shown this. Similarly, next question was also a theoretical one where we had proved f of a plus h plus is equal to f a plus h f dash of a plus theta h is nothing but limiting value become theta equal to 2, and so on. And the last problem we had find out the application of the theoretical problems. So, I believe that it will enhance your at least application of the Taylor's theorem. So, thank you so much.